Now let's look at mesh analysis, which is the other major analysis technique we're going to learn how to use. Now, mesh analysis is basically, as we're going to see, KVL plus Ohm's law, as opposed to nodal analysis, which was KCL plus Ohm's law. And as we're going to see, in some ways these techniques are kind of mathematical duels to each other in terms of how we're going to approach the solution to the problem. Now, the thing about mesh analysis is somewhat less versatile than nodal analysis, because mesh analysis really only works well on what we call a 2D circuit, a circuit that can be drawn on a piece of paper without any wires jumping over each other. So mesh analysis works fine for 2D. And 2D circuits are basically what we've been solving so far in all of our problems. Nodal analysis, on the other hand, will work with either 2D or 3D circuits too. Circuits that can be represented three-dimensionally. So for example, build a cube and then build the circuit that fills up all the edges and the inside of the cube. You can actually analyze that with nodal analysis. So mesh analysis, as we see, works on all the kinds of circuits we're going to look at in this course, but at the same time, it's not really as versatile as nodal analysis. So having said that, given the fact that nodal analysis can solve any problem that you can solve with mesh analysis, why do we bother to learn it? Well, as we're going to see later on, the reason why we learn mesh analysis is because with mesh analysis, some types of problems are easier. They give us fewer equations than if we use nodal analysis. And of course, the reverse is also true. Some problems are easier to work with nodal analysis than they are with mesh analysis. So between them, these two techniques essentially complement each other in terms of finding the optimal solution with the fewest number of equations. So let's kind of go through here now and let's look at an example of mesh analysis, and we'll see how we make the technique work and how we can do this with KVL plus Ohm's law. So let's start with the following circuit. Okay, so let's start with this circuit, and you could work this circuit with nodal analysis. I mean, you could work any of the circuits we've looked at so far, but this we're going to do a little bit differently. Okay, how do we make mesh analysis work? Well, with nodal analysis, we used the idea of the ground in order to give a node a particular value. In mesh analysis, we don't think about nodes. Instead, we think about meshes, hence the name. What do we mean by mesh? A mesh, very simply, is a loop that does not enclose any other loop. So in this case, if you look at this circuit, it's got 1, 2, 3, 4, 5, 6 loops, but it's only got 3 meshes, 1, 2, 3, because those are the only loops that don't have another loop contained within them. So what we're going to do is we're going to use, once again, a little trick. With nodal analysis, the trick we used was the ground. That was the way we were able to eliminate an equation so we could solve with KCL plus Ohm's law. With mesh analysis, we're going to use what's called a mesh current. So in this case, I'm going to define 3 mesh currents. And the idea behind mesh analysis is that we're going to assume that there is a current that circulates around each mesh. Now, these mesh currents may not actually correspond to any real current in the circuit. They may not correspond to anything you can actually measure with an ammeter. But by specifying these mesh currents and labeling them and using them the right way, we can solve the circuit using nothing but KVL equations plus Ohm's law. So in this case, I'm going to specify 3 mesh currents, IA, IB, and IC. Now we note, IA and IB, I drew clockwise. IC, I drew counterclockwise when I assumed it was flowing around the mesh. And here's the first thing about mesh currents. The direction you pick is arbitrary. So we define a current for each mesh, a mesh current for each mesh. We label it, and the direction we choose is completely arbitrary. So just as when we did KCL for nodal analysis, it didn't matter which direction we chose for the current. Same thing here. Doesn't matter what direction you choose. All right? Now, given these definitions, let's now go through and we're going to apply passive sign convention to all the resistors in this circuit. So let's see how we're going to do that. Okay, so some resistors have only one mesh current flowing through them. In that case, we're just going to use the passive sign convention. So for example, IA is the only mesh current flowing through the 10 ohm and the 2 ohm resistor. So according to the passive sign convention, those are the voltage drops across those resistors. Now over here, the 12 ohm and the 8 ohm resistor, IC is the only current flowing through them. Once again, I apply the passive sign convention. But now I've got this 4 ohm and this 3 ohm resistor, and those resistors span 2 meshes. So if we look at it, for this 4 ohm resistor, I've got the IA mesh current flowing through it here. I've got the IB mesh current flowing through it here. So for this resistor and for this resistor, the current in the resistor is a combination of the 2 mesh currents. Okay, what do we do about a situation where the resistor has 2 mesh currents flowing through it? How do we do the passive sign convention? Okay, let's consider this. So just to reiterate here, for resistors on the edge of a mesh, we're going to use the passive sign convention to define the voltage across it. For resistors that span a mesh, pardon me, I should say that span 2 meshes, first, if the 2 mesh currents agree they're going in the same direction through the resistor, we just use the passive sign convention. In that case, we're just going to use the passive sign convention. So let's consider the 3 ohm resistor. We note for the 3 ohm resistor, IB is entering the top, exiting the bottom. IC is entering the top, exiting the bottom. They're both going the same direction through the 3 ohm resistor. So I'll just use the passive sign convention. This polarity agrees with both of those mesh currents. On the other hand, if the 2 mesh currents have opposite directions, so for example, here IA enters the top, but here IB enters the bottom. They're opposite from each other. So if the 2 mesh currents have opposite directions, then we can choose an arbitrary polarity. We'll have to go with one or the other of the currents, so choose one. Then the polarity is arbitrary. So in this case, for the 4 ohm resistor, I've got 2 mesh currents going in opposite directions entering that resistor. I'm just going to arbitrarily pick. In this case, I'll pick that. Okay? So now I've gone through and I've specified the voltage drops across each of the elements. The resistor voltage drops have been specified. The voltage drops of the voltage sources are, of course, given. So now all I have to do is go through, and I'm going to write a KVL equation for each mesh. Now, in order to simplify things, I'm going to do a trick very similar to what we already talked about with nodal analysis. When I did nodal analysis, I told you guys, do nodal analysis with KCL plus Ohm's law. Same thing here. Let's do KVL plus Ohm's law. So I'm just going to go straight to that technique. So, for my IA mesh, I'm just going to follow the mesh current around that I specified. So in this case, I'm going to start here in this lower left-hand corner, travel clockwise, and going around the mesh, the voltage rises is equal to the voltage drops. So in this case, 10, which is my voltage rise, 10 volts, is equal to a drop. It's equal to 10 times IA, plus, now I'll come back to this one, but also plus 2 times IA, plus also this drop. So I have 3 drops. I did this one and this one. What about that drop? Now keep in mind I said that the currents are going in opposite directions. How do I specify that voltage? Okay, well, let's look at it this way. I've got a resistor. I've specified a voltage drop across it. So here's a 4 ohm resistor. And I've got IA entering the top and IB entering the bottom. But I want this to follow the passive sign convention. Clearly, IB does not follow the passive sign convention with respect to that voltage I picked. But I can fix that. Let's do this. Let's reverse this and call this minus IB. I'm changing the direction, changing the sign. Now the IB current follows the passive sign convention. Both currents enter the top of the resistor. So therefore, what is the voltage across this resistor? If I call this VR, what is VR going to be equal to? VR is going to be equal to 4 times IA minus IB. V is equal to 4 times I. It's the difference between those two currents. Therefore, I can now write this last one and say this is equal to 4 times IA minus IB. So that's for mesh A. Let's do mesh B. Mesh B, once again, I'm going to follow this around clockwise. Now this is a voltage rise, but it's still that value. But now it's just a rise, so I'm going to write it like so. 4 times IA minus IB, that's my rise, is equal to a 6-volt drop, plus, well, in this case, the two currents agree, plus 3 times IB plus IC. So in this case, once again, I'm doing Ohm's law. It's the sum of the two currents. They both agree going through that 3-ohm resistor. Finally, IC. In this case, I'm going to go counterclockwise. So starting here in the corner, I'm going to go around 12 times IC plus 8 times IC plus 3 times IB plus IC is equal to 0. And here I've gone and I've written KVL plus Ohm's law for the 3 meshes. I've got 3 unknowns, IA, IB, IC. Now I solve. And if I solve, what I will get is that IA is equal to 0.469 amps. IB is equal to minus 0.624 amps. And IC is equal to 0.0813 amps. Now, the point of mesh analysis is to calculate these mesh currents. Just as the point of nodal analysis was to find the node voltages, mesh analysis to find the mesh currents. Once we know the mesh currents, all other voltages across each element or all currents through any other element can be easily calculated. So once mesh currents are known, any other voltage or current can be calculated. For example, what if you were asked what I4 is? What is I4? What is the actual current flowing through that resistor? If you actually measured that with an ammeter, what would that current be? Well, I4 is clearly a function of those two mesh currents. In fact, once again, if we think of I4, I4 must be equal to IA minus IB, opposite direction. So once again, I want I4 to agree with the direction of those two mesh current elements. And therefore, I4 is equal to IA minus IB. And now I can go through and calculate that. That'll be equal to 1.093 amps. And there you go. So I can calculate the currents through either of these resistors. I can calculate the voltage across any resistor just in terms of a linear combination of these mesh currents. All right, so that's what we would basically call basic mesh analysis is what you would call this, okay? Just because we had basic nodal analysis. And we note that we can do this with resistors and with voltage sources, and you can easily solve these types of circuits. Okay? Now, in our next module, we're going to take a look at making these problems a little more interesting. We're going to add current sources to them. So remember, with nodal analysis, we started with current sources and then added voltage sources. Here we're starting with voltage sources, and now we're going to add current sources next time.